My name is Felix Linder. I'm heading a security consulting company in Berlin, Germany called Security Labs. We specialize in like the regular security consulting, security analysis work, mostly source code, binary analysis, and hacking of all types. And we also do design works, design verification, and secure system designs. But what we also do is research, and we're trying to make a point of making research that actually solves problems in contrast to academia, and that is actually practically applicable in the real world. And that's what essentially brings me here, because this is kind of an unusual talk. What I'm doing here is I want to describe to you where we come from in a certain research project concerning Cisco devices and what we've done so far. And the purpose of the talk is actually to collect your feedback on where we should go. So essentially, I'm standing up here saying, well, this is what we do, and now tell me what we do next. So let's take a short look on the agenda. As I said, I will briefly explain where we're coming from, then I'm going to briefly talk about iOS internals, how debugging and post-mortem analysis is done today, and then our new analysis approach and an initial public offer, or IPO, but like not for the venture capitalists, but for you, and then some future work. So where we come from is essentially IP routing infrastructure is like the way networks are built today. It's mostly based on v4. Slowly v6 is coming up, like as of the last 10 years. Next year v6 is going to be big. And one thing you have to realize is that when you're talking IP networks, it means that the nodes in the network, like the networking equipment, is intelligent nodes. You cannot build an IP network with stupid nodes. You can build it with like stupid operating systems, but not with like stupid nodes. They have to make intelligent forwarding decisions. IP is based on the fact that each node only knows the next hop. And even if you try to prevent that and you build like full flat networks, you get a whole lot of different problems, as was experienced the hard way by people when they set up cable modem networks and DSL networks. So what does that mean for the security? Like, we have IP, which by itself is inherently naive when it comes to security. So we put all sorts of security protocols on top of that. The goal is to guarantee that they have end-to-end integrity and confidentiality. And they can like think about SSL or IPsec. They can detect modification. They can find you replaying or injecting traffic or holding traffic back. That's all solved. And then they inform the upper layer. Now the thing is, neither the protocols nor the upper layer can do anything about it. Like, if you find yourself in a situation where your encrypted communication is tampered with, that's it. You can stop communicating, or you can go on and click on, yes, I accept that certificate. There is no way that the security protocol or any other instance on your end host can influence the routing. So if you find yourself in a situation where one of the boxes in the network actually makes something you're not agreeing with, you're essentially fucked. Which brings us to the point, what's the infrastructure looking like? We do have something like an infrastructure monoculture. It's not mono as in just one single thing, but it's mono like in Windows operating systems on a desktop. There are people running something different, but like most of the infrastructure we're looking at is Cisco systems routers. And it's like, they're equivalently distributed over all types of networks: government, internet core, corporate networks, even small home networks, and so They have many different hardware platforms, but what has to be realized is there's a very large sum of money bound to that equipment. This equipment is not cheap, otherwise Cisco wouldn't be such a good stock to invest in. So it's really hard to replace. Even if you resolve to not run Cisco anymore, it's going to cost you a lot of money to replace all the equipment and put something equally shitty from a different vendor in. And the thing about Cisco is they all run more or less the same operating system. So we have this infrastructure, and I think I made it clear that we think it really has to be protected. And to protect it, we first need something that allows us in-depth analysis and allows us diagnostics on this infrastructure. Otherwise, we're just flying blind. So speaking of the operating system that runs on all the boxes, Cisco Inter-Network Operating System. It's, again, a very monolithic operating system, but like when you look at the landscape of Cisco iOS, it has something what I call a three-dimensional complexity. You have platform-dependent code that, yeah, as the name suggests, is dependent on what platform you run, like what type of router, what type of CPU is in the router, what line cards do you have, stuff like that. Then you have feature set dependent code because they don't give you all the features right away, but they have comparable to Windows Vista. There's the home version, and there's the professional version, and there's the ultimate version, and there's the broken version. And the same with iOS, but you have a lot more combinations. And then you have major, minor, and release versions. It's actually 3 version numbers right after each other. And then again, you have something that's not even on the slides, which is trains. So you have the main train, and then you have the technology train, which means you get the new features, but they guarantee even less about how well they work. And then you have some other trains, which ends up being you have tens of thousands, actually, like in production in real life networks, you have over 100,000 different iOS images used today. Which, and like, last counting I did was like 18, what the hell? Okay, like 18,000 of them actually still are in support. That sucks, I don't see the slides. Let me see if I can fix that. Did work. So what's iOS looking like? Now, iOS is, in the regular case, it's a single large ELF binary. So essentially, it's a large statically linked Unix program. You know, it's called operating system, and it does show you processes and stuff, but it is essentially a very large Unix program. And what happens is there is a piece called ROMon in the router, which is kind of like a BIOS on your PC, and it finds the image and starts this ELF program. And then this ELF program runs, as long as it pleases to do so. It runs directly on the router's hardware, and due to the fact that they support or actually use different types of CPUs, and due to the fact that it's a single program, it doesn't use any of the protection features the CPU provides. This could be explained by the fact that they would have even more platform-dependent code if they would actually use the protection features that the CPU provides, like supervisor and user mode on a MIPS, or memory protection, paging, memory segmentation, something like this. But it's actually explained by the fact that they never had to. They never cared about it. What the hell? So, the processes I mentioned, like when you go onto a Cisco router and you say, like, show processes, it will actually show you processes. They will have nicely like process IDs, and they will look like real processes, but in reality, they're actually like more like p-threads. And if you ever work with p-threads, you know they suck. The same holds true for the processes on iOS, because there is no virtual memory mapping, and it's essentially the only thing that differs between one process and the other is the CPU context where it's running it, and that's about it. They have a run-to-completion cooperative multitasking scheduling. If you remember Windows 3.1 and Windows for Workstation, and you remember like looking at the hourglass for hours and nothing happens, that's a run to completion scheduling. Like the operating system cannot interrupt a single task and say, you just eat CPU cycles like crazy. I put you on hold and someone else is going to do it. But it actually waits for the task to finish and say, okay, I'm done. And well, of course, that has some problems when you're routing packets because you cannot anticipate when the packet is arriving. And what they do here is interrupt-driven handling, pretty much like you wrote network drivers on MS-DOS. So that also means, since it's a big Unix program, it has system-wide global data structures. Like all the data structures work system-wide. They have one common heap. They have very little abstraction around the data structures, reason supposedly being speed. But I think the real reason is that they never introduced it, so the coders don't use it. And there's also no way to force abstraction. If the coder chooses to write directly into one of your main system's data structures an arbitrary byte value, he can do so. There is nothing preventing him except for maybe another coder reading his code and then punching him into the face. I've seen like small snippets of leaked iOS code, and the most entertaining part are the comments. They're actually like, they have blocks of comments in the code where they are threatening their colleagues. If you ever change this piece of code, I'm going to hunt you down. Because they have no technical way of enforcing abstraction. So why is that a security issue? Now, if you take a 12.4.16.8, that's just a random, fairly recent iOS release with the enterprise-based feature set, so that's not even everything included, but like half of everything, we're talking 25 megabytes of code in binary. That's a lot of code, and that's a lot of things that can go wrong. This is for a 2600, so of course the number of bytes changes based on the CPU. And that's not counting like the firmware for the line cards and for initialization and what have you. So this is for a small router. We're not talking like big iron here. Everything is written in C, which we all know is the language that allows you to most elegantly shoot yourself in the foot and like at the same time hit your head. It's all sharing the same address space, the same heap, and the same data structures, and millions of pointers pointing anywhere they want to. So that means a single mistake in the most unimportant piece of code can influence anything on a system, including kernel, security subsystem, cryptographic code, firewall code, what have you. Even if you, and Cisco managed to do that, even if you fuck up something as simple as the UDP echo service that's supposed to like take a UDP packet and send it back. If you do that and you fuck it up, the effects will be that something will write somewhere, anywhere in this big Unix program and you don't know where, which is of course a very, very desirable situation for any attacker. Because he doesn't have to look on like the SSH daemon or something running on high privileges to find vulnerabilities and exploit it. If he finds a vulnerability in like the finger service or the NTP client or totally useless features like voice XML programming for your fax port, then he will have, once he got code execution on that one, he got code execution on a same thing, on a whole thing. It means instantaneously remote kernel. So obviously the question is, well, Cisco should be aware of that. I mean, it's a big company, and I'm sure there are many people that don't deserve the job they have in there, but there are also smart people. So of course Cisco is aware of that. And the fact is they're a marketing-driven company, which means they rewrote iOS about 6 times. And 6 times marketing said, it doesn't have the same features that like the old one has, so stop working on a new one and extend the old one, please. And they finally got around a few years back to actually get something out and get over marketing. Also forced by the fact that Juniper is actually running a more or less real operating system, FreeBSD. So they do have real processors. So there's iOS XR, and iOS XR is a commercial QNX microkernel-based operating system. If you ever looked at QNX, it got plenty of its own problems. So I think they just made sure that they don't buy code that has higher quality than their own. It does have real processors. I'm not entirely sure if it has memory protection, but it is designed to be a real-time operating system. So it's not fancy about like the inter-process protections. It's more built around like fast scheduling, which is probably the reason they actually use it. But it has significantly higher hardware requirements. Not the kernel by itself, QNX is really small. But of course they put like a few thousand additional features in there. So like you can't run an iOS XR on your existing Cisco gear that you have. And then again, people don't upgrade iOS. They never do. I mean, they do everything, including sacrificing their mother, before they upgrade the image version they use in a big network installation. When I talk to my customers that actually run big Cisco networks, they are told by Cisco's own engineers to not go beyond 12.2, while 12.5 is the current version. And 12.2, just to like keep things in relation, is something like release time before 2000. So it's not really new. And that only speaks about people that have a networking team that knows what they're doing. That doesn't speak about like the many, many networks, corporate networks, even ISP networks that were having Cisco gear placed into their network, fired up, running, and then forgot about it. So the question would now be, well, talking about something like iOS, just like how often do routers really get hacked? Like, is that a problem, or is this fat, short German guy making up stuff on stage? Well, in the keynote, we heard about a complaint that people would not update their routers and that it was cause for concern. But do you know how expensive it is to actually upgrade from one iOS version to another? You have to upgrade all the routers, which means you have to put more memory in there. If you want to keep warranty, you have to buy the memory off Cisco, which of course means the chip that would be really, really cheap off Infineon or Kingston will be everything but cheap because it has a Cisco logo on it. And of course, you also need to upgrade the software, which of course they don't give you for free. And between one minor release and the other, the configurations don't port. They look the same, but they don't work the same. So you actually have to test essentially your ass off for half a year to see if like how you have to adjust your configurations once you switch from one iOS to the other. Old vulnerabilities, like there was a bug in the HTTP server, and don't even ask me why they have an HTTP server on a router. Many years ago, that allowed you to get administrative access, and that's still actively scanned for. Like it still shows up in typical honeypot sniffs and IDSs. And people actually, those are more like the script kiddie types. They use the routers as a jump pad because the routers have many interfaces. They usually have pretty good location in the network. Sometimes they're also used as the firewall itself, so they can just like turn off the firewall rules. And then in like the bigger installations on telco networks or big corporate networks that already run newer versions of iOS, the new versions have TCL scripting on the shell, and TCL supports binding to a port. So next thing you know, people were building TCL backdoors for years because they were just so useful. The router would, arbitrarily refuse to let you in because like the AAA server was down, or the radios was like puking around because it was a loosened radius or something along those lines. And then they had a TCL backdoor on some high port, and they could just telnet in and have full privilege. That got recently published. So it's now common knowledge, but it's been used for about like 5 years, I guess. And then there is the issue with patched iOS images. Now, I mentioned that iOS images are not cheap, and they don't come for free. And so if you buy a router, you usually buy a router with a basic IP feature set, which means it can route IP. But if you want to have SSH because your security officer insists in you not telnetting around your network and providing high privilege passwords, you actually have to buy an additional feature, which means you have to buy a new image because they're hard linked. So you have to buy an image supporting crypto to support SSH. Now that costs a lot of money and many people refrain from doing so. And we have like a file sharing effect here. They would just search the internet or ask people, do you have an image for this and that router type, this and that feature set, this and that hardware? And then take this image and roll it out. But patching images is actually really, really easy because they're a big program. They have a few interlocking checksums, but that's not a big deal. They're all CRC. So you can just recalculate them. There is no crypto involved. And then they just use some image that they got from God knows where. And then there is lawful interception, which has to be a good thing because it's lawful. But it has the problem of the router's operator is not supposed to know that lawful interception is actually going on. So you have actually quite a lot functionality in the router that's remotely controlled and fairly privileged because it can redirect traffic and you don't see it, which raises the question, who watches the watchers or who makes sure that the lawful interception is actually done by an agency that is from your home country. So what about the future? Is that going to be better? Well, nobody's changing the infrastructure. And on the other hand, ever notice that attackers are really lazy pack? They look for the target where they can, with the lowest efforts, get the highest return of invest. They're a lot better than most managers. In Windows becomes a pain in the ass. Seriously, finding remote ODA for NT authority system privilege level on Vista is a pain in the ass. And that's seriously, you can see that when you look at the prices for ODA, what's paid for a remote IIS exploit. And Unixes are hardened. Even Apple starts to harden the fancy little clicky OS. And then infected PCs are the cheapest way right now, client-side attacks. Just infect a whole bunch of them and hope that one of them is in the company you're actually trying to attack. So far, it's the cheapest thing. But they leave obvious traces. Even the German government managed to find finally some Trojan in their Bundeskanzleramt, which is pretty much like the White House. They managed to find the Chinese Trojan after God knows how long they had it. So the question is not really, will routers become a target? But the question is, or in my opinion should be, do we want to know when they do? So in summary, we have a significant share of the internet, governmental and corporate networks running on one of several tens of thousands of builds of more or less the same code base in a single process environment. And if something goes wrong there, we can't even bypass it, even if we knew that it was compromised. Which brings us to the next question, can we even tell if it's compromised? So how does error handling and recovery work? The software architecture I lined out dictates how you have to handle exceptions. Remember, it's a Unix process. So what does a Unix process do when it seg faults? It dies. And in the best case, you have a cron job that's restarting it. So the same actually happens on iOS. Upon an exception, if something goes wrong, iOS can only do one thing, restart the entire router. Even onboard checks, they have checks for the heap structures and some sanity checks here and there. Even if they have, if they do diagnostics and they find an issue in the structures, something that's not correct, the only thing they can do is what they call a software forced crash, which essentially really is running a trap and rebooting the machine. Reboots are a very clean recovery method. I mean, you power cycle something, that's usually the last resort, and that's usually like the best way to get it back into a known state. The problem is reboot also destroys all the volatile data and evidence of the crash cause. So everything on a router is volatile. So you don't have swapped out data. You don't have a hard disk. Except for the startup configuration that it obviously needs on the flash to boot, and the iOS image itself, everything else sits in RAM. So when the box reboots, everything is gone. So you wouldn't find out what happened. Later iOS releases actually write an informational text file. It's called crash info. The thing about crash info is it contains very little information because it's a small text file, right? And well, the contents that are put into crash info depend on what iOS actually thought was the cause of the crash, which usually leads to very useless information. Here's an example. Like, it's probably a bit confusing, and believe me, I cut all the bullshit out. If you look at that over here, the stack trace, and you have done something with exploitation, you would probably notice that someone was smashing the stack here successfully. Now, then you get like tons of heap dumps and memory dumps of all types of process contexts and stack contexts. And they usually don't have any relation to what really went wrong, because at the point where it overwrote the stack and the return address here, iOS totally lost track of who actually it was. And then it will try to give you a partial decode of the process information block on what went wrong. Now, funny enough, it will say it is the crash writer, which is exactly the process that started to write crash info. So it is actually reporting itself as the offending process, while obviously I can tell you it was something totally different. You can also see that the process didn't exist for very long because it doesn't even have any runtime information over like 5 seconds and 1 minute, so it was just started. This is how informative and useful crash info is. Now, and then we have the question of runtime evidence. Like, crash info is only written when the device comes down the hard way. Successful attacks, by definition, don't cause device crashes. You know, the device is supposed to stay online and provide you with a vector or whatever your purpose of attack was. So you have some available methods here. It's show commands, debug commands, SNMP, and syslog, and I'm going into those. So show commands. iOS offers a lot of commands that start with show. And it's really a plethora of commands. There are many, many of those. And of course, they change over iOS versions. So once you learn them for your one router, you upgrade to iOS version, forget half of them, and learn them new. And of course, it requires access to the command line interface. If your router goes crazy, you can't log in anymore. And it's, of course, geared towards network engineers, so they can show you all types of routing tables, ART tables, whatnot, but it wouldn't show you like much about the process contexts and like what process probably had a pooch stack or something. There are many, many different versions, and then there is almost no access to information that would be interesting for a forensic expert. Up to 12.3, they still had commands that would allow you to say show memory and then OX something and give it the virtual address in memory. In 12.4, they actually removed this, probably to counter reverse engineering, which I'm entirely sure really didn't help them at all. Right, Hover? And then you have debug commands. Debug commands essentially enable verbose mode in different parts of the code. Now, I mentioned the code is kind of huge-ish. So you have a debug command for pretty much every single function or group of C functions that they run through. And then debug commands have scheduler precedence, and they said it's a run to completion scheduler. So if you have too much debug output, the router just stops working and keeps printing until the buffer is empty. And then it goes working again, which of course means your TCP session are all going to waste. Which also means it's not an option in production environments. Like on big telco networks, if you're debugging something, what they usually do is they tell the router to reboot in 5 minutes. And then they start debugging. And when the debugging goes wrong and the router like chokes on itself and the debugging messages, they just wait the 5 minutes because they told the router beforehand to reboot. That's the only safe method to do remote debugging on bigger telco networks. And then like debugging output, like have the right debug command for the right thing is an art. If you turn on the wrong ones, then you don't see shit. And you turn on too many, the router stops working. Which commands to turn on, again, depends on the iOS version, down to the release and train. And of course, for debug commands to be useful, you have to know before things happen that you want to see something. So there is no way to say, turn on debug commands back in time. Of course not. It's a verbose output feature. So that's not very useful to find out if your router got compromised or not. And then SNMP and syslog monitoring. SNMP is commonly accepted the method to manage and monitor your networking equipment. It depends on the implemented message information base. Like most of you have seen that, there's a MIP, and the MIP describes what counters, strings, tables are provided to the management system over SNMP. And then if Cisco didn't implement something like process list or process information in a MIP, you wouldn't see it, which is the case. And syslog on routers is about as useful as security monitoring as it is on Unix. You usually see like all the interesting things like login worked and someone downloaded the file, but you're not going to see a syslog message saying, yeah, process just got owned. Both generate traffic, and both are actually as useful as the people reading the log files. I don't know how many people here in the room work in an organization that has people dedicated to reading log files. You do. So it is quite rare. And then it is quite questionable if they would actually like understand that something goes wrong when they see it. So to sum it up, identifying a compromised router with the today's tools is essentially impossible. There's just not enough data to perform postmortem analysis on router crashes, and it doesn't really matter if it's security related or not. And we can't distinguish between a functional fault, which is unfortunately very, very common, an attempted attack, or even a successful attack on iOS boxes. So we just don't know. Which brings me to our idea how to solve that problem. What we need is the maximum amount of evidence that we can possibly get. So essentially, a full memory snapshot is just enough for us to work with. On the other hand, we don't need that every 5 minutes. We need that either when we have suspicion about the device or the device came down. And then we need something independent and preferably solid to analyze what we got. And that should be extendable. What are you smiling? So how do we get the evidence? iOS engineers essentially have the same problem. They get all the crash infos from customers. They claim they're like trying to figure out what happened, but obviously with a little text file they can't. So they try to reproduce the crash, and then they want a full core dump. So iOS can write complete core dumps, memory dumps. It's a big Unix process, so it can core dump. It can dump core of the main memory, of the I/O memory, and if it has of hardware-specific memory, like PCI memory. And core dumps are written in two cases. Either the device crashes, or someone issues a command, which is write core. Supposedly, that's just to test if the device can actually write core files to the destination, but here it comes in really useful because it fulfills the requirements we had for obtaining evidence. So where does a core dump to? I mentioned it doesn't have a hard disk, luckily enough. it supports various destinations. So you can core dump to an FTP server, which is the preferred method, an RCP server. Later versions can even core dump to the flash file system, which is notoriously filled up with clutter like iOS images, and crash infos. I've seen the latest version actually has like a crash info aging feature, so you can tell it to delete the crash infos continuously if they start piling up. So, and it could theoretically write core to an TFTP server. However, Cisco's brilliant implementation of the TFTP protocol does not take into account that when you have a block counter in a protocol that's 16-bit, you can hardly expect a block of 65,536 to arrive at the router, which is what they implemented. So they implemented the block counter in a 32-bit integer in code, but it's 16-bit on a protocol. So on a protocol, it wraps. In a code, it doesn't. So everything that's larger than 16 megs cannot be dumped by TFTP. So it's not a valuable option to write anything. The bug is known since 12.1 and was promised to be fixed soon, which didn't happen yet. Core dumps can be enabled by configuration. The 2 points below here might look silly, but they're actually quite an exception in iOS. The configuration commands do not differ between iOS versions, and the configuration change has actually no effect on the router's operation or performance. As I said, that's very rare about a feature that you turn on. So my idea was, how about a core dump enabled infrastructure? You go ahead and you configure all your iOS devices to dump core onto one or more centrally located FTP servers. That minimizes the amount of monitoring you have to do on the router. Essentially, you don't even have to monitor it all the time for being up or down, which you do by polling. But you just see if a core dump materializes on your FTP server, and then you know the device crashed. It preserves all the evidence, and it allows crash correlation between different routers that you have. Like if in 1 minute your FTP incoming directory was empty, in the next minute you have 20 core dumps from 20 different routers, something is going really, really wrong in your network. And it's probably faster to see it that way than waiting for HP OpenView to get off its ass and blink red. So the question is, why doesn't anyone do that? Like, even when I talk to highly respected Cisco specialists, they say, well, yeah, we have tons of crash infos, but we don't have core dumps. Well, the reason being, the core dumps were useless except for Cisco engineers and exploit writers. So now we have to make the core dumps useful. Analyzing core dumps, here's a short disclaimer. Everything I say here is can be done with published information, some of which I'm guilty of. And I would talk about our implementation of the core dump analysis, but of course, choose your own weapons. I mean, you can do that in Perl if you want. So what requirements do we have? First of all, it should be independent of Cisco, because you don't want to have the person that's potentially guilty also leading the investigation. And you don't want to base your analysis on any disassembly of the image you're analyzing. Of course, you have to reverse engineer some of the data structures, but you don't want to use the data with the disassembly together because, well, the code to begin with was, what the hell? Was causing the problem. And then on the other hand, disassemblies are not perfect. And then we must gradually recover all the abstractions. So we get a flat memory core dump, and we have to get all the data structures back and see what iOS was about to do and what it fucked up with. We should not make any assumptions, and we should be able to cope with massively corrupted data, because that's what happens when people overflow your buffers. And then again, I mean, it's silly to say it, but I've seen so many forensic tool sets and other stuff written in C and being as vulnerable as the stuff they're trying to investigate. So preferably, we're not writing this in C and we're not shooting ourselves in the foot with a nuclear warhead. So how do we get the abstraction back? The first thing is we use the image, the iOS image that was supposed to run on the router, of which we have a copy not on the router, preferably. And in a worst case, we can just go to CCO, the Cisco server, and download a fresh copy of the image. And we use that as a memory blueprint because the ELF information contains the information we need for the memory mapping. So we know how the memory was mapped that we found in a core file. So essentially, the ELF file serves as our blueprint for the core file to see where things belong to. And then if we already have an image in a core file, we can do a very simple and very effective analysis, getting rid of all the patched images. Because we can just byte to byte compare the read-only data section and the text section of the ELF file and the core file. And we will know if the image was patched or not. It's a really cheap method, but it provides us with a very high level of assurance that the image was not compromised before it was even loaded on the router. And then we go ahead and reconstruct the entire heap. iOS, as I said, uses one large heap, and it contains plenty of meta information and metadata. Most of it actually for debugging purposes, because iOS engineers don't really have a way to figure out what went wrong, except for the heap blocks being smashed up in a certain pattern. They're like, if they look at a big heap of debris and rumble, they will tell you, okay, it was a 1960 Ford with a female in a blue dress driving against a Mercedes C-Class, because that's all they can do. And that's what they use the debugging information in the heap for. So up to 12.3, we have 40 bytes overhead per heap block, and then 48 coming 12.4 and later. Apparently, some of those that were added were a feature for preventing buffer overflows forever, which worked as well as you would expect something like this to work. Reconstructing the heap essentially allows us to perform very extensive integrity and validity checks. iOS has onboard checks, a process called check heaps, that walks the heap chains and looks if they're like consistent. But the tests are very limited. Well, the reason being the router is usually busy to up to 80% CPU usage forwarding packets. That's the damn purpose of the device. And that's what you paid for. So they cannot waste lots of CPU cycles on integrity checks. So check heaps is as thorough as it can be, excuse me, on a router that has very limited resources to do stuff like that. Now, when we reconstruct a heap, we can do whatever we want. We have the full power of a desktop machine, and we can take as much time as we want because we're not forwarding packets at the same time. And we actually have a decent operating system on the bottom. So we can implement the full functionality of check heaps, which is really not that much. And we can also find holes in the addressable heap. Now, holes in the addressable heap are invisible from check heaps because it walks the chains. And they're not supposed to be there by design. They're only there if evil people overwrote pointer pairs and executed a successful heap overflow attack that resulted in code execution. We can also identify other heap overflow footprints, like heap overflow that failed. Values overwritten in the headers that are not inspected, in the fields of the header that are not inspected by check heaps, but that are overwritten by values that are very exploit specific. There's, for example, one field that has mostly 0 bytes in it, and with a classical buffer overflow and a string operation, there will be something else in there. And if you find something like this, iOS is not even capable of writing something else in this field. So you know something went wrong. We can map the heap blocks to the referencing processes. We know from the meta information in the heap what process allocated the block, what process freed the block if the block is free, and what his name was. So we can actually build up a graph and see what processes access which blocks and get something like a reference count on the blocks, which could prove to be interesting. I don't know. And we can identify formally allocated blocks. Even in the supposedly free memory, we can see the leftover heap block headers, and identify processes that used to eat a lot of memory. Because often with iOS, you have the problem, and that's not a security problem, it's a pure functional and network operational problem. One router starts choking and has not enough memory to let you in again. You try to telnet into the machine and it just tells you out of memory, I'm sorry. And 5 minutes later, everything is fine again. You log into the machine and then what? You can't see what happened. Now in this case, you could write core and then see what heap blocks were allocated 5 minutes before and who did it. Because it could be an indication of someone doing route flooding on your machine or something else. And then, of course, we reconstruct the process list. The process list is essentially a central array, and it's the data structure that they use to manage their so-called processes being threads, which enables us to identify the process stack block and create individual per process backtraces, not just one that iOS thought would be relevant, but backtraces for each and every process that was running on the router. In which way we can actually identify return address overwrites. Because if there is a return address on the stack that was just used, so it is above the stack pointer, which points into code that's not related to the process that the stack is related to, it stinks. We can obtain the process scheduling information, which again helps finding processes that misbehaved. The CPU usage and the CPU context, like the full CPU context. And we can essentially do almost everything in terms of postmortem analysis that we know how to do on a regular operating system for like a Unix process, because again, it is something like this, given those two items, a reconstructed heap and a process list. And then we find TCL backdoors. That's really simple. We just walk the heap, find the blocks that belong to the TCL scripting engine, identify those that contain a TCL script, give it a name, and dump it into a file. And then someone more intelligent than a piece of code can look at them or grab over them and look if they say bind port or listen to port. Very easy. Yeah, there is about the TCL scripts, I mentioned them before. There was a known bug till, I think it's 12.3 something, that if you have a router that uses AAA authentication, which means it uses a central authentication server and not local passwords, which is a typical telco setup, and you started a VTY session, you telneted into the router, and you started a TCL script to listen on a port, it was supposed to be terminated when you terminate the session. But the AAA correlation with like the VTY session, things get ugly if you don't have processes and abstraction. So they essentially forgot to terminate the TCL script when you lock out the router, which gives you a way better way to implement more backdoors. So we can extract all the, that's funny, TCL script chunks. It says TCP script chunks. I'm obviously a networking guy. So that's more or less the state of the art on the process forensics side of the routers. So as I said in the beginning, I'm here to ask for your wishes and feedback. So this is some of the stuff where I think I can claim we can extract that within a reasonable amount of time without leaning myself too far out of the window. So there's just some examples of things that you could ask for, like tables of interfaces, static routing, the state of the router processes like OSPF, decision tree, OSPF state machine, BGP bearings, VLAN tables, VPN contexts. If you lost your VPN shared secret, we can extract it. IPv6 tables of whatever sort, ARP, dialer, CDP, spanning tree, access lists. One thing that I find really interesting, because Cisco had many bugs in that area, is reconstructing the Ceph tree. I'm not going to comment on it anymore. So reconstructing the Ceph tree would be really interesting. The Ceph tree is the Cisco Express Forwarding, which sounds like they bought a subproduct of FedEx. It essentially means it's a B tree over the IP addresses, and they use that to speed up forwarding, as the name suggests. Now, their common bug is if something is forwarded based on Ceph, they keep forgetting looking at the access lists. So if the router also serves as a firewall or packet filter, it happened quite often that they realized that some types of access lists were just not looked at, because the router would go, wow, I have a Ceph entry and this is hardware accelerated. Go, out, boop, packet gone. Access list goes like, what packet? They had about like 5 or 6 different bugs in different hardware platforms with the same thing happening. So it would be really interesting to like decompile the ACL and then extract a Ceph tree and find if there is a matching where the Ceph tree actually will have a routing entry where the ACL would actually prohibit it, because you would automatically find other filtering bugs on iOS. We could extract user sessions. We could find port binding code that's not running in the text section. So if someone actually managed to like inject code and have a port binding shell, there is a single data structure on iOS that you have to register your callback function with. Otherwise, you wouldn't get a port bound. And you can essentially go into this data structure and see if the callback pointer actually points into the text segment that you already verified. If it doesn't, it stinks. And it actually already points to the shellcode. So you can automatically extract whatever clever shellcode someone came up with. That would be a feature that we'll probably implement anyway. But then there's more. iOS forwards packets, of course, based on its memory. There are different forwarding mechanisms, and I'm just glossing over the details here because it's like packet forwarding is the stuff where the Cisco engineers actually know what they're doing. So there's process switching, which essentially means like loading stuff into main memory, asking the main CPU to decide where the packet goes, blah, blah, blah. That's the slow path. And then there's fast switching, particle systems for fast switching, and hardware accelerated switching of all types and flavors. And when Cisco says switching, they mean routing. Except for hardware switching, all use I/O memory. So I/O memory is written for a reason in a separate core num, because it essentially tells you the state of what the router did on what data it operated to the time it dumped core. By default, on a shared memory router, which means the small boxes, about 6% of the router's memory is dedicated to I/O memory. It's just like separated. In real-world installations, they actually use a lot more memory, because the more I/O memory you have, the faster you can forward. Because the more I/O memory you have, the less you have to move stuff around and overwrite. On hardware-switched platforms, you get PCI memory. That's, as the name suggests, sits on a PCI bus. And even that is written in a separate core dump. So when we look into those, we see that the routing and switching buffers are actually ring buffers. And they're not one big ring buffer, they're different ring buffers of different sizes. So you have ring buffers with small buckets for very small packets. You have some for medium, some for large, some for huge. And then interfaces have their own ring buffers for locally handled traffic. Like if traffic comes in Ethernet 0 and is supposed to go out Ethernet 0, then it's not copied anywhere. It stays in the ring buffer of the interface Ethernet 0. And iOS code in general tries really, really hard to limit memory I/O, not copy the packets around like a Linux or any other operating system, but like keep the frame in this one piece of memory and just pass pointers around, because copying the packet is going to take time. So that all means that new traffic does not necessarily overwrite older traffic in a linear and predictable, well, in a predictable, yes, but not in an expected way. It means that if you have lots of traffic on regular TCP packets, like 1400 bytes, it will all end up in the medium buffers. While if someone is sending bigger stuff or smaller packets, they end up in different ring buffers. Now, what we can do now is extract the traffic. What we do is we identify the packet structures that are handling the process switching on iOS. We could do more, but we wanted to do that first because that's fairly interesting and needed to be shown that it can be done. So we identify the structures that point into I/O memory, and then we take the I/O memory sections and essentially just dump them into a PCAP file. So you can look back in time at the traffic that was forwarded through the router or sent to the router. Which, of course, stuff is process switch, as I said, when an access list matching happens, or if you have QoS, it needs to look into the TCP header and see what port it went to. And as I said, we could also dump packets from other memory regions, and we could reconstruct the fragments more thoroughly, because right now we're just like taking the piece of memory that is supposed to be the buffer element and then dump it into the PCAP file and don't care about the size. This is how it looks like. It's a regular PCAP file. The only thing that you will notice is that the time is 0, because that's a piece of information we didn't extract so far. And I don't think it's actually recorded. I don't think it actually writes a timestamp when a packet arrives, because it would just, like the 32-bit write would probably take longer in main memory than it would on a hardware accelerator platform to push the packet out again. But we can still like find lots of traffic. And you see here, like the one selected is, I think it's a telnet session. Yeah, it is. With some output that was coming out of the router when I was logged into. So we can do some more with the traffic extraction capabilities. The thing is, writing core to a remote server, of course, uses I/O memory, because I/O memory is used to handle packets, and writing something to a remote server means producing packets. So it overwrites part of the traffic evidence we're looking for. There are two ways: either have a really big flash card and dump core to the flash, but that would be rare, and that would be counter my argument that, I mean, if you invest in new hardware for the Cisco, you can just like invest some more and get an iOS XR. Assume that's any better. I didn't actually look at it yet. But what we can do in a kind of like emergency situation where we really want to preserve all the traffic data is we take the undocumented GDB serial link to the Cisco. There is like this GDB serial protocol is for remote debugging embedded devices or other devices. And so what you can do, or what you're supposed to do, is connect to the console and turn on GDB debugging on the serial port. And we do support the Dynamics GDB debug link that was developed for BinNavi to debug Cisco devices. Now we can use it to obtain all the memory dumps and actually work on that instead of the core. It's abstracted away in SIR, so we don't have any difference there. But it halts the router, so it preserves the evidence a lot better, even than writing core. So what can you use with that? Well, obviously you can identify attack jump pad routers. Like if someone used it as a jump pad, you just dump core and see what the guy was, where he came from. You can do something like a better IDS. It doesn't cost you anything, but like once the machine behind it got owned and it's segmented off on its own interface, If you're quick, or the exploit happens to be in a different size of packet class than all the other regular traffic going to that machine, let's say it's a big buffer overflow and the machine is regularly a DNS server handling small UDP packets, then you just dump core and you get the packet, which means you get the ODA, which means you know what you're looking for. And if you're really bored, you can backtrack people that spoof traffic because, well, on an Ethernet level, dumping the information, you know what interfaces the frames came in from and what interfaces they came out with, and you just follow the cable till you run into the guy that's sending the spoofed packet. And then what I find mildly amusing is you can detect if someone is doing lawful interception on your device and where the traffic goes to, and you can, ping the feds. Challenges we're facing, and one is obviously missing from the slide, which means lots of reverse engineering and like waiting for the processing of the reverse engineering to happen. We have to handle the whole complexity of the iOS landscape. So we have to handle all the hardware platform image versions in an any-to-any relation. Because nothing is more useless than an analysis framework that doesn't do decent analysis, right? Right now, our implementation is feature set independent, so we don't have to have any information on what feature set this image was on. We have successfully tested this stuff on the 12 series iOS, and we're currently supporting two smaller access level routers for two reasons. One is the nice sounding reason, because we think that the access level routers are way more often attacked than the big core routers because they're less protected. The not so nice but honest reason is we just don't have the money for the big gear. We're going to support 3600 and 7200 later. That's in the process. And again, your wishes, if there are even any, we'll decide the course where we go here. Now, in summary, we think that writing core dumps is a viable method for obtaining iOS evidence when it's needed. And the evidence includes, as we just saw, received and forwarded packets. And an independent analysis can actually distinguish between the things that we couldn't distinguish before, bugs, attacks, and can do real forensics. And we can already reliably identify many types of attacks and backdoors on iOS, so we can finally tell what the state of the infrastructure is. So this is the initial public offer, essentially. So the quality of an analysis framework lives and dies with the amount of cases it has seen. I mean, we can produce some cases in our labs. We can, put some backdoors in, but honestly, detecting your own backdoors is kind of cheating. So we need more food for the SIR to grow, and we also want to provide it on a long-term basis for free. So there is a service where you can essentially upload core files, and it will, in the backend, use the latest SIR version and produce a report for you. But please be gentle, it's really the alpha version we're talking about here. And given enough interest, there will be a professional tour, but that's probably way in the future. And as I said, the purpose of the talk was to see if anyone finds that interesting. We think it would be useful for networking engineers, for forensics, and to finally figure out how much of our infrastructure is already owned by dollar government. We can think of way too many things to implement that would be fun to see. Then we have time and resources to dedicate to the task. So please help. And that was it. Questions?
It's my understanding that the newer Cisco routers that are based on Felix, they don't have serial
I've not seen a Cisco router that doesn't have a serial interface. Have you seen one? It goes fully against the concept of Cisco. No, I've not seen a single Cisco router that doesn't support GDB debugging over console. Yes, and yeah, that's where we realized we have terms of service for the service set up. That's what I did yesterday. I made sure that it includes non-disclosure. But of course, if someone offers us a heap of production core dumps in exchange for an NDA, that's like the easiest thing to do. We would definitely do that. We totally realize that. I mean, I just mentioned we can extract VPN keys. So people would probably be reluctant to give the keys to the kingdom in a core dump to us.
Have you heard anything about iOS moving to FreeBSD?
God, no. No, they just came out with, like, the XR is pretty new, and then they have NX on a Nexus I've seen just like recently, of which I don't know what to make of it. I don't think they would move to be FreeBSD. Okay, but I mean, Cisco is having so many products now in their range, and they have bought so many companies. I can easily assume that they're following a totally different track on a totally different product platform that has nothing to do with iOS routers. Because if you just look at people that like ran Linux on iOS hardware or on Cisco router hardware, it's just so crappy, and it's just like so not usable. Just from the architecture point of view, it doesn't really work. So I would actually, like, your guess is as good as mine, but I would really guess it would be a different product line. Yeah, we've been asked that. Well, the subline cards are, as much as I've seen it, like Cisco keeps claiming, oh, this is all our proprietary like firewall feature card and stuff. If you look at them, they boot a Linux, which is not really proprietary. But apart from the GPL violation, I think we would. We don't have the gear right now. I'm pretty convinced we will pull full images of the routers, because what I assume is the Cisco engineers are going to want to dump all memory that's mapped, and that will include line cards. If the line card is just interfacing on a bus and working independently, then we will probably not get the information. On the other hand, it also means it cannot be compromised or harder. Yeah. Well, then it should be able to dump core. But frankly, we have not seen the equipment to actually like perform the tests and compare the memory maps with what we get on the core.
So I ran into this new exploit in terms of core dumping.
Congratulate you. Of course. I mean, there's no analysis method that you cannot circumvent. You can also, I wouldn't even turn off core dumping. I would just mask out the memory that I just placed my exploit in from the core dumping and would replace it with some like Hello Bunny ASCII art. So of course you can, like, it core dumps either something goes wrong or someone initiates writing core. But then again, if you extend your exploit as far as preventing it from writing core, then it should be, well, you increase the chance that your exploit goes wrong. And I mean, we're still talking many different platforms and iOS flavors. So yes, it can be done. I'm not saying.
It's also you said, okay, you just want core and don't monitor anything else anymore. Maybe then explanation would be more successful. So you can at least see systems going up and down without core dumping.
Yeah, but on the other hand, like the management overhead is so big in like real big networks. What they really do with SNMP is burn some large percentage of the CPU power of the boxes, and especially on the access layer, it's not necessarily a good idea. So, but if you exploit a machine and it doesn't dump core anymore, then we can still walk up to it and use the GDB link to get your not core dumping exploit of the machine and see what it did. Okay, thank you.